Just 3 of you gone, right? 4 of you?
Four.
Wait, what's going on?
The test that doesn't matter unless you're going to.
Let's take more tests.
Well, that's why we stayed
Yeah,
there.
yeah.
That's why we went.
Is that why? Or?
No, I just wanted to keep chugging along.
Yeah, we'll only have a little bit of 5th hour, 6th hour, 7th hour, 8th hour.
We'll probably take the day off tomorrow. Maybe I'll do some standardized test practice with you guys.
I already took the ACT.
Oh, you're supposed to go, sorry.
Who told you that?
Because they're indebted, dude. I used to do it ironically.
They really are idiots. The people who do AP are really stupid. Because they literally the first the very first AP exam is chemistry. Like you could have put like Japanese language and culture on that day. So like essentially you would have to take the AP chemistry test like 3 weeks before we're even done with the material. Does that make sense? So it's just Ben, right? You don't have to. I'm just giving these to you.
Alright.
You can take any of these, right? Like you don't have to be in the AP class.
We need to pay to take the test.
Like I could take Spanish literature and culture if I wanted.
Yeah,
You
we're
could.
prepared for that.
No, I'm just saying.
I'll take
Japanese language and culture. Yeah,
Honestly.
See, it's like they put one of the hardest AP exams day one. I've never had anybody take the AP test just because it's usually easier to just take the CLEP route. The CLEP test is a lot easier than the AP test. And that's usually in the summer, so like you've gone through all the material. I did have Aaron Bush take the CLEP. Did your sister take the CLEP? Probably not, she just retook it.
I just want to take all of these and see how well they
Yeah,
do.
just waste $1,000.
Yeah, I wouldn't actually.
This is like $100 a test or something crazy, yeah.
Yeah, they're not cheap. The club is about the same actually.
Yes, but the CLEP is easier.
Right, but like U.S. government and politics, I feel like I could take that. Maybe not get a good grade, but not enough to pass the test.
In the future, I'd like to actually go full AP, but in order to do that, I'd probably have to start the class like 2 weeks before school started.
Don't you have to like be trained to JP?
But
Isn't Mrs. Safford the only one that's actually qualified to JP so far in her school though? They have to like be qualified
yeah,
to do
because
it.
it's exponentially easier to do AP English than AP
Yeah.
chemistry. Just because
You just have to
of
say what you're doing.
lab times. I mean,
Yeah.
you know, when do I have time to do a 3-hour lab?
You got kids.
No, I'm not talking about that.
Like with class time.
That would take like
So your clock can't get today.
I meant like after school. You can't do it after school because you have to. Imagine just
Hey, college professors don't have kids.
No, I know, but you can do it after school.
I would love to teach in college because you only have like
A class.
an hour, like 3 hours of teaching a day, if that. Although then you've got your research stuff and whatnot. but-
Yeah, is most of what college professors do, would you say teaching or more like research?
Depends on what, if you're talking about big Division I schools,
It's more research.
95% of their time is research. And they pretty much just have graduate students teach their classes.
Yeah.
Alright.
And so like getting to the actual professor who knows the stuff really, really well is virtually impossible.
So, yeah, why do you even call them
I'm
Do they-
call them researchers.
professors? Yeah.
Or
Do they teach
or
any
experts.
classes?
I don't know for sure. I'm sure they teach some graduate
Like
level
graduate,
classes
yeah.
maybe. But
Isn't that their job
Because-
to teach?
no, their job is to research to make the school money. That's how they. That's honestly what. Because schools get huge grants
Yeah.
for research.
Yeah.
And so the school has, gets these super smart professors to do research so that they can, that's how they make their money,
What research and literature professor do though?
I have no idea.
Like uncovering
Research.
ancient books.
I don't know.
Just a mausoleum, just rip open a door and book.
Yes,
History teacher.
but they don't have time, they've got kids. Alright, so we're going to talk in this chapter. You're going to see a lot of very familiar vocabulary words, starting with the reaction mechanisms. And if you remember seeing this, it is really the series of steps that make up an overall chemical reaction. So when we've been doing chemical reactions in everything that we've done in chemistry, that's really just the beginning and the ending of the reaction. Does that make sense? Okay, it's what you start with and what you end with, and there's no information about how it got there, and if it was multiple step reactions to do it, or if it was a one-step reaction, there's none of that information that's ever given. Which, for the purposes of a lot of things, that's okay, because they're state functions. But for the purposes of rate, you have to look at the steps, because you're only going to be as fast as your slowest step. And I'll give you an analogy a little bit later today that will help you kind of comprehend what this would look like from a chemistry standpoint. So let's say we have, I'm going to pull out a new marker. I'm feeling fresh today. Ready? Got this. Yes, so smooth. Do you have space? Okay, so there's your balanced chemical equation, which it's more complicated than this. It's not just this produces that. It's more complicated. In fact, here's what the determined differential rate law looks like. For this particular reaction. As you can tell, the first reactant is second order. What's the second reactant? What's the order of the second reactant? Zero order. How do you know that? Because what? It's not there. Okay? So, what's interesting about this is that this guy, changing its concentration has absolutely no effect on the rate, and I will show you why. Okay? This is the believed mechanism. Step one. Step two. And they're each going to have their own constant. We could find the rate laws of both of these. Okay? Does anybody know what these steps are called? Nope. Did you look quickly or you remember?
No, I remembered as I was looking.
Yeah. Okay? So these steps are called elementary steps. Okay, so I kind of clump them like the whole thing is elementary steps. No, each step is called an elementary step. If you take the whole thing, all of the elementary steps, what do we call that? The reaction mechanism. And if it's more than a one-step reaction mechanism, we could call it a complex reaction, which I don't think I even have that in here. Okay? Do you remember intermediates? Do you? At
Yeah,
all?
like NO3 would be an intermediate.
Okay, so that's an intermediate.
Oh,
Okay, there is there one more? I'm trying to think.
No, everything else is just the game.
I mean, yeah, you could kind of call this an intermediate, but you also still have one. Okay? Now, on the next slide, okay, so there's intermediate. So, if I were to look at this, this was determined to be the slow step. This was determined to be faster. Okay, do you remember the name of the slow step, what we call it? Good, 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 good. We call this the rate determining step. Okay, and why do we call it that? Okay, because it determines the rate. Now, if you look at the rate determining step, that means our rate law is going to be dependent on this particular step. And an analogy that I could give you for why the reaction is only as fast as the slowest step would be just imagine you were pouring water rapidly through a funnel. What determines how much water is going to go through the funnel? How much you pour in or how much the funnel will let through?
How much the funnel will let through.
So you could have one step just pouring through. But if it's only getting things at a rate through a funnel, or the opposite, it's only going to be able to do so much. Okay? So the slowest step is going to determine the rate of the overall balanced chemical equation. Well, let's look at this slowest step. Okay? What don't you see in the slowest step? In correlation to the rate law. And why that makes sense. What?
Zero.
Yes, this is not in the slowest step. So if you change the concentration of that, are you going to be affecting the slowest step at all? No, and that's why it doesn't appear in the rate law. Does that make sense? Okay, now open up your books. Page 563. We're going to look at something known as molecularity. All right, so top of 563. All right, so yeah, so what molecularity is it by definition, is kind of a goofy definition, but it says the number of species that must collide to produce a reaction represented by an elementary step. Okay, and you can see in that table that there's a few examples. There's unimolecular, there's bimolecular, there's termolecular. Okay, termolecular is the most difficult and least often seen, because you have to have 3 molecules that all collide perfectly with the correct amount of force and so forth. So because you have so many reactants there, it's considerably difficult for all those to collide at the same time. So a lot of times you don't necessarily see a rate determining step that looks like that. Okay? Now, molecularity is this idea that if we're studying the steps, we can figure out the rate simply by the coefficients. Do you remember the very first chapter, or very first section, where I gave you an equation and I said you cannot just look at the coefficients to figure out the orders? Okay? Because you can't, because we don't know if it's a one-step reaction or not. Okay, but you can look at your rate determining step and determine the molecularity, or determine the order from its coefficients. So if I were to look at this, this would be the same as saying 2NO2, right?
Yeah.
You see it? Okay, so it gives some examples here. If you had A plus A, you would get A to the second. If you had A plus B, you would get A to the first, B to the first, because that's what their coefficients would be, and so forth. Okay? So let's say I gave you a reaction mechanism. Would you be able to very quickly write the rate law? If you knew what the rate determining step was, absolutely, you could just do it by looking at the coefficients. However, it's very difficult to come up with a reaction mechanism. In fact, we're going to find out in a sec that there's no way to 100% prove if it is a correct reaction mechanism. And why would you not be able to 100% prove the steps?
I don't even know if it's the same every time.
That's true, you wouldn't know that. But why wouldn't you be able to prove
Because it happens like that.
true? And you can't see it. Like, in a balanced chemical equation, you can see what you start with, right?
Mm-hmm.
And you can see what you end with, correct? You don't really see what happens in between. Alright? So, there are a couple rules that will help us here. Get rid of that. Okay? So, first thing. In order for a reaction mechanism to even be a viable option, you have to be able to take the sum of their steps and get your overall balanced chemical equation. Do you remember doing something similar to this with Hess's law? Where if they were on opposite sides, what could you do with them?
Yeah.
If I were to rewrite this, isn't this my balanced chemical equation? Okay, so could you have a reaction mechanism that fulfills this and probably fulfills this and still be wrong? It's possible, okay, because we have no way to prove it, okay? But we know that if it doesn't fill these two things, it can't be possible. Okay, the second thing is the mechanism must agree with the experimentally determined rate law. What that simply means is your slowest step of your mechanism must agree with your rate law. From a molecularity standpoint, where I said we were able to look at the coefficients of that and it agrees with our rate law. Does that make sense? So in order for it to be true, or in order for it to be a possibility, you've got to be able to cancel them out and get your overall balanced chemical equation. And second, your rate law must agree with your slowest rate determining step. Right? And even then, you can't 100% prove it. I want to read a short section of this. Flip the page, one page here. We're almost done. Okay, I'm going to read the last paragraph before we get to your reaction mechanism problem there. Okay? How does a chemist deduce the mechanism for a given reaction? The rate law is always determined first. Then, using chemical intuition and following the two rules given on the previous page, the chemist constructs possible mechanisms and tries with further experiments to eliminate those that are least likely. A mechanism can never be proven absolutely. We can only say that a mechanism that satisfies the two requirements is possibly correct. Deducing mechanisms for chemical reactions can be difficult and requires skill and experience. We will only touch on this process in the text. So I'm not going to make you try to come up with a reaction mechanism. But I am going to make you take a reaction mechanism and maybe write a rate law or see if a reaction mechanism is a possibility, okay, which is what I want you guys to do here. Okay, so it gives you an overall balanced chemical equation. It gives you the experimentally determined rate law, like we did the second day of this lesson, where we had a bunch of experimental data and we did the compare game, and we saw how the concentration changed with the rate. Okay, and then it gives you a suggested reaction mechanism. I want you to tell me, is this an acceptable mechanism? Or in other words, does it satisfy the two requirements?
Not this Saturday, but the next one.
Yeah. So yeah, I haven't gotten a single game back yet.
What?
I'm glad you guys enjoy playing, but I don't understand it at all, or enjoy it. Kramer's gonna blow up the pop can.
Yeah, this is for you guys, sorry.
Oh, this one?
Yeah, I remember.
Yeah, that's that one.
It didn't work, actually. So
They're gonna do it the next day though, right?
yeah, I think so.
It's really embarrassing when science doesn't work.
I remember I couldn't see what happened. I remember you put a pumpkin on a heater, or no, it's not a heater. Like, what is it? I don't remember you putting a can on a thing. I don't remember what it was.
So
What is it? It's like-
what you do is you boil the water, which causes it to evaporate and produce gas that's in here. And when you invert it into a cold reservoir of water, it compresses
Right.
the gas, relieving the pressure that's pushing out from within the can, and then the atmosphere just crushes it.
Okay, yeah. Remember not being able to see. But yes, that makes never mind. I remember that now.
And I must have either not inverted quickly enough, or I didn't have it boiling enough that enough gas was, yeah, I'm not sure. So, alright, quickly, what'd you guys get?
Yeah.
Okay, so you should have been able to cancel these out so that you got this, correct?
Yeah.
And then you should have looked at the slowest step and looked at the molecularity to make sure that that rate law agreed with that, which it did. Okay, cool. Tomorrow we'll do some more Excel stuff. Actually, we won't. On Friday.
Do we graph any of them today?
Nope.